This is the first chapter of the electrodynamics, and in this we will discuss the basics of mathematics, which includes the differential calculus, integral calculus, curvilinear coordinates. Our today lecture includes the differential calculus. In the differential calculus, we discuss the ordinary derivatives, gradient, del operator, divergence, and curl. So we start from the ordinary derivatives. We discuss the ordinary derivative of any function fx or fxyz. Suppose this is the function. Mathematically, function has some properties we should obey it. Mathematically, the definition of function is df over dx limit. Here is the del x approaches to 0, fx plus del x minus fx divided by del x. Here fx plus del x minus fx is the change in the fx. This is the change in the function. If you change the argument x plus del x. Del x is the change in x. So df over dx is the rate of change. This is the change, and we divide it with the del x, so it becomes the rate of change with respect to x. So ordinary derivative df over dx is also the slope of any function. Graphically, we can represent the different types of the function. Suppose a function which does not change with the x, we can say that this function is constant with respect to x, so its derivative will be 0. And another function which value uniformly changes with the x, this function is not constant, and its derivative is constant because rate of change is constant. This function is varying, and also its derivative is varying. So we can say that is derivative change, rate of change is not constant in this function. So these are the different examples related to the derivatives. So its derivative is 0, derivative is constant, derivative increasing. Negative derivatives, negative rate of change. If any function value decreases with respect to x, then such change is negative, and therefore these derivatives are called the negative derivatives. Positive derivatives, if the value of function increases with respect to x, these different graphs 1, 2, 3, 4 represents that value of f increases with respect to x, and slope of such function is positive, and we can say that ordinary derivatives of these functions are positive. Slowly varying derivatives, small change of function. Suppose a function value changes with the x very slowly, like this. change is very small with respect to x, such functions, such derivatives are slowly varying derivatives. Next, we discuss the another type of different in differential calculus, which is the gradient. So gradient of scalar function, we take the gradient of scalar function. Mainly there are the two types of the functions in mathematics, vector function and scalar function. So what is the scalar function? Scalar function is a scalar quantity and it depends upon the space coordinates. It has the different examples such as the temperature, pressure, density, because these physical quantities vary when with respect to coordinates. When you move in space, these quantities may vary. So these are the scalar function, and also these quantities are the scalars. Vector function, we denote it with the v, x, y, z, and this vector function depends upon also space coordinates. These vector functions are electric field, magnetic field, velocity. So these functions vary with these space coordinates. Del operator on the scalar function t, x, y, z. Del t, this is called the gradient of t, and it is defined as curly t over curly x into x cap plus curly t over curly y into y cap plus curly t over curly z into c cap. And these derivatives are the partial derivatives. So you must know the difference between the partial derivatives and ordinary derivatives. In the ordinary derivatives, any function depends upon only one coordinate. If any function depends upon more than the one coordinate, such as the x, y, z, then derivative with respect to some particular coordinate are called the partial derivatives. Suppose function f, x, y, z and its change in f. This change in f we can calculate in this way. Suppose you know the partial derivatives of x with of function with respect to x, and you multiply with the del x. Del x is the small change. Then you can calculate the change in f. Similarly, if you know the derivative of function with respect to y and you multiply it with the del y, you can calculate the change in f with respect to y. And also, if you know the derivative of function with respect to z and multiply the del z, which is the change in the z, so you can get the change in f due to change in z. So to calculate the total change due to change of all these coordinates, you can write in this way. You can add all these changes and get the differential change. df is equal to curly f over curly x dx plus curly f over curly y dy plus curly f over curly z into dz. Using the dot product rule, a dot b ax bx plus ay by plus az bc, you can write it ax into x cap ay into y cap plus az into z cap dot Bax x cap plus by y cap bz into z cap. Because when you will take the dot product, then ax bx will be equal to ax bx. X cap dot y cap will be 0. X cap dot z cap will be equal to 0. So you get only this term when you multiply ax and bx, ax and this b vector. And you multiply ay and this b vector, you get this. Multiply az and this b vector, you get this. So in the previous slide, we have calculated this differential change in t, and we can write this differential change in this way according to this product rule. Partial t or partial x into x cap plus partial t or partial y into y cap plus partial t or partial z into z cap dot dx into x cap plus dy into y cap plus dz into z cap. In the previous slide, we have defined the gradient. This factor is the gradient of t. So we represent it with the del t, and this is called the infinitesimal displacement, and we denote it with the dl. So dt is equal to del t dot dl. So this is the important equation. If you know the gradient of t and you multiply it with the displacement, infinitesimal displacement, you can get the differential change in the t. From this equation 1, del t dot dl, del t dl cos theta, according to the dot product rule, a dot b is equal to ab cos theta. Let's fix the direction of del t and vary the dl. When you vary the dl and fix the direction of del t, theta is the angle between the del t and dl, and when you vary the direction of dl, it means that you vary the theta. So for some particular direction of dl, del t is along in the direction of dl, and in that case the theta is equal to 0, and in that case dt is maximum. So dt is the maximum when dl is along the direction of del t. So we can write the direction of del t is the direction in which the change of t is maximum. So physical meaning of gradient, we can discuss it in two ways. What does tell us the direction of gradient? What does tell us the magnitude of gradient? The direction of gradient tells us is the direction of maximum increase of t. So direction of gradient is that direction in which the increase of some scalar function is maximum. And magnitude, what does the magnitude tell us? We know that the dt is equal to del t dot dl. So we can write it in this way, del t dot dl into l cap. dt over dl is equal to, we divide on both sides with the dl, so you get dt over dl is equal to del t dot l cap, and if you multiply on both sides with l cap, you get dt over dl to L cap is equal to del T. If you take the magnitude uh, of this equation on both sides, del T, magnitude of del T is this, and magnitude of dt over dl to L cap is this. So magnitude of del T tell us the rate of change of T with respect to L, with respect to infinitesimal displacement L. So magnitude of gradient of some scalar function gives the rate of change or slope in maximal direction. What is the maximal direction? Maximal direction is that direction in which the change of T is maximum. So in this direction, the gradient, magnitude of gradient tells us uh, the rate of change. We can explain this in this way. For example, we take the scalar function of height. Suppose and this is the mountain, and you take the position of mountain, this position of mountain, and here at this position the different slope when you see around you at the top of this mountain, the slope varies in the different direction. In this direction, this is direction 1 and this is the direction 2. Can you tell me in which direction the slope is maximum? Definitely the slope is large in this direction because steep is very high. On the another direction, the slope is very small, rate of change is very small, height, change of height is very small. So what will be the direction of gradient? Here we will decide what is the maximal direction. What should be the maximal direction? Maximal direction would be in which direction the change of height is maximum, and that direction is this. So this direction is the direction of gradient. What is the meaning of del T is equal to 0? Del T is equal to 0 mean the rate of change is equal to 0. Rate of change of some scalar function is 0. And this del T is equal to 0 represent the summit or valley. So what is the summit? The maximum height of some scalar function where the change of scalar function is 0, and these points are also called the stationary points at which the change of some scalar function is 0. So if you have this scalar function in this way, so these points represents the summit, these points represent the valleys. So here the change of T is 0. Now we discuss the example 3. Find the gradient of r is equal to x square plus y square plus z square square root. This is the magnitude of position vector. We are going to find out the gradient of r. Solution. We know the definition of del T is equal to partial t over partial x into x cap plus partial t over partial y into y cap plus partial t over partial z into z cap. In this case, the scalar function is r. So t is equal to r is equal to x square plus y square plus z square square root. T is equal to x square plus y square plus z square raised to power 1 by 2. We can write the square root equal to power of 1 by 2. So what is the method to solve the gradient of t? So you must solve the first term, then second term, and then third term, and then to find the gradient of t you will add all these terms. So we will take the first term, curly t over curly x of t. This is the t, and curly t over curly x, this is the value of t. So we take the gradient of this t with respect to x. We apply here the power rule, curly t over curly x. The power rule is we write the power which is equal to 1 by 2, then we write the function, and we subtract 1 from the power. 1 by 2 minus 1 is equal to minus 1 by 2, and then we take the derivative of this equal to 2x. And similarly, the partial derivative of t with respect to y are 1 by 2x square plus y square plus z square minus 1 by 2 into 2y. 2 will be cancelled. Partial t or partial z is equal to 1 by 2 x square plus y square plus z square raised to power minus 1 by 2 into 2z. So gradient of t is equal to, we take the sum of, we put the values of curly t over curly x, curly t over curly y, curly t over curly z in this equation, and you will get this. This is the value of curly t over curly x. This is the value of curly t over curly y. This is the value of curly t over curly z. In the denominator, this value is equal to r. This is equal to r. This is equal to r. So you can write del t x cap divided by r, y cap divided by r, z cap divided by r. If you take the r common, then you will get x cap plus y cap plus z cap, which will be equal to r vector, and you can write r vector divided by r is equal to r cap. Thank you. In the next lecture, we will discuss the remaining topics.